Hello students, we are going to continue our introduction module with a quick look at some of the great ideas in computer architecture. To name, very first one is design for Moore's law, second being use of abstraction to simplify design process, third idea is to make the common case faster, fourth idea is achieving higher performance with parallelism, fifth being achieving higher performance by pipelining. Sixth is achieving performance via prediction. Seventh is deploying a hierarchy of memories, again to achieve performance. And eighth is dependability via redundancy. So let's look at each of them now. The very first one is design for Moore's law. What does Moore's law state? It states that the resources in an integrated circuit will double every 18 to 24 months. It means for every 1.5 to 2 years, the resources in the integrated circuit, basically the number of transistors, will double. This was proposed by Gordon Murray. He was one of the founders of Intel. And it was basically an insight that he derived from one of the prediction which came out in 1965. And even though it is called as a law, it's not a law per se. It was just a statement made by Jordan Murray, and it so happened that all the companies in the semiconductor industry took it upon themselves to make this statement true. So eventually it became a law. What is the direct impact of Moore's law is, for every 1.5 to 2 years, we will have twice the number of transistors. It means that we can use those transistors to integrate more and more functionality onto the same chip. And in process, we can also achieve higher speeds. Now, another way of looking at it is, let's say we have a small chip with dimension 1 mm cross 1 mm. Let's say a couple of years back it had 100 transistors. Now, after 2 years or maybe 1.5 years later, now we have 200 transistors in the same area. So because of that, even though we are able to include more functionality, the area is being same. It means that the mobile phone, which had a limit, which had some capability 2 years back, will now have better functionality because primarily because of the technology scaling. Like I said, the entire semiconductor industry tried to catch up with it, and in the process made it true. A quick example is here. Almost right from 1968 also or so till the current year 2020-2021, you can see on the y-axis that transistor count, how it has increased. So you can see almost all the companies here, starting with Intel, Motorola, AMD, and of late you will see some IBM processors. There's a DEC processor here, there's an ARM processor here. Everything, almost all the companies tried to catch up with it, and they made it a reality. Now if you look at the one of the process here which I did not touch till now, it's called an IPU. It's basically an abbreviation of intelligence processing unit. Just like we have GPU, TPU, CPU, etc., we have IPU. What IPU specifically does is it will try to accelerate machine learning algorithms. So if you're um, more interested, just Google for IPU processor. Okay. Now, if we look at the one of the latest GPUs, it has nearly 24 billion transistors in it. If we specifically look at how Intel has progressed trying to catch up with the Moore's law, so at present, in the previous one of the previous lectures, I mentioned about Intel Core i9, which is fabricated at 14 nanometer technology. It had somewhere between 6.5 to 7 billion transistors. Now the 10th generation of Core i9 almost has 10 billion transistors in it. That has come out in 2020. So the Intel company as such increased the number of transistors almost as if it was guided by the Moore's law. With more and more functionality on the same area, we are able to get better and better products. Moving on, the second idea was use of abstraction to simplify design. Now, this we do almost in our day-to-day life. What it basically means is we will try to abstract out the design so that we can work at a slightly higher level on a slightly bigger problem. So, for example, the computer system stack that we saw a couple of lectures back is a good example of abstraction. All the software developers are abstracted from the hardware details by one layer or another, popularly the compiler, because when we write a program, we don't write it specifically for x86 processors, means Intel processors or AMD processors or IBM processors, etc. The compiler, which is specifically built to one particular ISA, will handle that. As programmers, what we do is we just focus on the logic and efficient implementation of that logic. The same with the architects also. Of course, now because of accelerators coming to the picture, we are making a tailor-made hardware for one particular program or a set of programs. But in general, when we design a laptop or a desktop or any server, we don't design it for one particular program. We design it so as to handle any generic, uh, any day-to-day program, and when we use a appropriate compiler, we should be able to run it on this hardware. The third idea is to make the common case fast. Now this is again one of the very popular things that we do in our day-to-day life. Now if a quick example is, if you know that one particular question um, is repeated multiple times in the previous question papers, you'll definitely go and study it. That was the common case. One set of question or one type of question is repeated, so that you anyways do, right? And also another way of looking at it is, when you were preparing for any competitive exam, you would definitely look at how the overall grading is bifurcated, and you'll focus on something which will give maximum number of marks, right? So the same way our hardware is built. If we are trying to focus on general purpose machines, for general purpose machines, we will design the hardware that will make the common case fast. Now, how do we identify common case? Again, it's dependent on the end product. Why we would need to make the common case fast is basically the number of transistors, even though it is increasing, they are still limited. We don't have an unlimited number of transistors at our disposal. So to make best use of whatever we have, we'll try to focus on something that happens very frequently. Now, there can also be a few cases which are not common. Let's say, let's call them as outliers. And if we are dedicating much of our hardware resources to those outliers, what happens is our regular programs or regular cases get affected. So instead, the trade-off would be try to dedicate enough resources for the common case, and only the extra or additional resources would be dedicated to handle the outliers. So in the process, we might not get the best performance for the outliers, but we still are able to get decent performance for the common case. So after the um, module 1, we are going to look at the instruction execution, where we'll get to know the terms fetch and decode. There we'll realize that those fetch and decode units are used more than a typical multiplier unit or an adder unit, etc. So if we want to optimize that particular instruction execution, it's better to focus on fetch and decode units rather than on a multiplier unit. The fourth idea is achieving performance or improving performance via parallelism. Again, you all are well versed in this. If we have enough resources, we should be able to use all of them for getting something done faster. For example, about the p-threads concepts in Java, or in general the software threads. What does it mean? Is a single program is logically divided into multiple threads, and each thread is run on a different core, so that overall the program execution becomes faster. At the system level, we can say that if we are able to parallelize the task and involve multiple processors and multiple disks at the memory, then we would be able to get better performance. The major limiting factor is scalability. For example, if you try to divide your program into 10 threads, maybe the performance is 10x. But when you divide it into 20 threads and try to run them, the performance need not be 20x. It might slightly drop. It depends on the way the program is written. The term used is called scalability. Within an individual processor, if you look at it, at the core we have pipelining for handling instruction level parallelism. If you're not able to completely get it at this moment, it's okay. We are going to discuss in detail about instruction level parallelism in module 2. At the cache level, we have multiple banks, and each bank can handle a independent request on its own, so that overall we'll get the data faster from the caches. Again, if you don't get it yet, it's okay. We are going to look at this particular uh, technique of multiple banks in module 3. Now, from your digital logic class, you would already see that within an ALU, if you want to deploy a carry look ahead adder, the major performance benefit we get is because of the data level parallelism. Multiple adders are working on multiple different data items to get the result faster. And in the previous live session, I have also made a point about GPUs and TPUs, primarily designed to exploit data level parallelism, wherein we are performing one or a group of operations on multiple data items in parallel. Moving on, the fifth idea is achieving performance via pipelining. Again, this is very commonly used. For example, in your a mess, you have multiple counters. Let's say each of those counter uh, having multiple counters, you can say, is the parallelism part of it. But within each counter, you will have one the food items placed one beside another. So the you when you pass by, there will be one person in front of you taking the food item which is right next, and there will be one person behind you who will be taking the food item that you have just crossed. So that way we are able to service, or multiple persons are able to fill their plates simultaneously, but each of them is filling the plate with a different food item. Like I said, instruction pipelining is one popular way in computer architecture how pipelining is used, and we also have out of order processing. This would be typically part of advanced architecture course. Another method of improving performance is using prediction. Again, uh, prediction is a very generic method that we use. For example, to get the weather prediction, based on that we plan our travel, right? And that or a similar prediction mechanisms are used at multiple places in your processor to get better performance. The primary takeaway point is it is better to guess and move on rather than to wait for the exact outcome. So this we will realize in module 2 when we are going to look at some branch prediction techniques. So branch prediction, load and value prediction, prefetching, speculation, all these popular techniques are based on the concept of prediction. And the prediction would work as long as the penalty that we are going to pay in terms of time or power or area is less than the case where we would have gone wrong. In case we go wrong, we should not be paying too much of cost, like I said, either with time or power. Moving on, the seventh idea is deploying a hierarchy of memories. In module 3, we will we'll see the real impact of memory on overall performance of the processor. And to address such a critical concept, the architects have introduced a hierarchy of memories instead of having a one big chunk of memory. So this hierarchy of memories was also an answer to one of the most uh, you know ideal expectation of memory, which would be very fast and which would have almost infinite capacity, but at the same time it should come at a less cost. So we are going to deal more about this concept in module 3. It is primarily based on a very intuitive principle called principle of locality. What the principle says is programs or the applications that we write will reuse the data and instructions very often than usual. What it means is if we are able to keep the data and instructions that are being reused closer to the processor, then the overall performance would increase. A very popular observation is typically a program spends 90% of its time on only 10% of the code. One popular example that we can give is loops. In a typical program, much of the time is spent iterating over a loop. This is the most common observation. Moving on, the eighth and last great idea that's very popularly used, very predominantly used in architecture is dependability via redundancy. Now, again, this is not a totally new or out of the blue kind of idea. Even we use it in our day-to-day life. For example, we take a spare tire with us whenever we are traveling, uh, specifically, especially for the four-wheelers, or even some of the two-wheelers have an extra tire. Now, that's one case. And another popular example that I can quote is typically, if you look at the landing gear of an aeroplane, there will be multiple tires for each of the leg, if we may call, right? In case even if one tire fails, the other tires will still be able to sustain and land safely, right? In general, any physical device can fail. So in an eventuality that it fails, what to do? The most common solution is redundancy. It means that take a copy of that and keep it ready. So the redundant resource will kick in when the primary resource will fail, right? And one of the popular example is RAID memories. RAID expands to redundant array of independent disks. We are going to look at it again in the memory module. And a couple of lectures back, I was mentioning about Tesla's self-driving computer. It had two chips, right, working in tandem, distributing the load, and in case one fails, the other will be able to still handle the overall uh, computing requirement. So with that, I'm going to pause this lecture now. In the next lecture, we are going to look at what the performance of a computer really means. I've been using the term performance a lot in this lecture. Right now, it's just a term. Now, we don't know what exactly it means, how to measure it, and how will it help us to compare one computer to another. We are going to look at all these aspects in the next lecture. Thank you.